Hello and what's up to you all, Mindsetters, Greater and Mindsetters. It is a lovely Tuesday and I hope that you've been having a great weekend, Easter weekend and the family day, of course, yesterday. Let me know how did you spend it with your family. Otherwise, my name is Abram and I'm with Tracy. Tracy, how are you?
I'm well, thanks, Abram. How's it, Mindset? It's good to see you. Welcome back. Welcome back from hopefully a really blessed Easter weekend. And Abram, as you say, family day. Very important to have some good quality family time.
What did you do, Tracy?
Church, and had a really, really good time. Just relaxing at home with my husband and starting to get our baby room sorted because baby's on her way.
See, you have to make sure that everything comes in handy and you're ready for everything. But otherwise, I'm glad you enjoyed yourself. What are we doing today?
Mindset is we're going to be tackling physical and chemical change. And physical and chemical change is all about chemical reactions and helping to identify when something is going through maybe a change of phase or state. So a physical change versus a chemical change. So very helpful foundations we're laying in chemistry.
Awesome. And you know what? Because we're talking about the Easter weekend, during the Easter weekend, we've reached our 75,000 likes, which was our target.
Wow, that's awesome.
That's so awesome, and thanks to everybody, but most importantly, the teachers that make everything possible. So we just want to appreciate you, Tracy, from Mindset, and we have something special for you. So this is just for you.
Woohoo! Thank you so much, Abram.
You're
That's
welcome.
brilliant.
You're welcome. So,
Yum.
so for you Mindsetters who are not on Facebook, make sure that you go to facebook.com/learnextra. Like the page, share the page with everybody, your friends, your schoolmates, your classmates, your neighbors, even your teachers. So tell them about Mindset. Follow us there, also on Twitter @learnextra. And lastly, you can download your notes on learn.mindset.co.za. But to make things more special for you guys and simpler, we have the download links for tonight's notes. So it's 2 links. It's the direct links to view the notes and another link to download the notes. So all those are on Facebook. I'll be posting them right now. We also have the challenge question, which Tracy will tell us more about. But to make things more even fun, because we like giving as Mindset, we have this awesome competition whereby we're being sponsored by Casio. We're giving away these awesome calculators. All you need to do is to take the test yourself questions, which the link will be on Facebook where you can submit your answers. So there is a form that you need to fill in with the right answers. The first person that gets the right answers wins this awesome calculator. Closing time, it is tomorrow at 4 p.m. Tracy, back to you.
Thanks so much, Abram. So Mindset, as we said, physical and chemical change. And in this lesson, we're going to be discussing differences between physical and chemical changes. And so always helpful to be able to identify through the differences, we can identify what we mean by physical and chemical changes. And so it helps us to identify from a description, maybe they could give you like a whole little sentence, which one would be a physical, which one would be a chemical change. And then we're going to be discussing the law of conservation of mass. Okay, and also the law of conservation of atoms. And that's very helpful because we'll be talking a little bit about what we mean by conservation of matter, what we mean by conservation of mass, and conservation of atoms. So it should be very helpful. But I want to challenge you because it's always about thinking. As Mindset is, we want to challenge you to be thinking. And so I've got a challenge question for you here, and it's specifically linking to a bit of practical work that you need to imagine and think about the setup and consider answering some questions. 2 students in a lab investigate the heat conductivity of various metals. Now, by heat conductivity, we're meaning that we're going to have some warm kind of source. So I've got a Bunsen burner, and how it conducts heat. So these different metals, how they conduct heat. We're dealing with metals, and you should note metals are pretty good conductors of heat. They set up 4 metal rods. Okay, that's useful. Of the same length, and attach matchsticks at the end with small blobs of Vaseline. So I'm going to draw roughly what I would picture. There's a little rod, and we've got a matchstick at the end. That's a little matchstick that's attached to the end with a blob of Vaseline. They set up the rods equal distances from a Bunsen burner and use a stopwatch to time how long it takes. So that could be useful for the Vaseline to melt and then cause the matchstick to drop off the rod. Identify the independent variable in this experiment. Identify the dependent variable. So we are considering here variables, independent, dependent variable, and very important that you can identify which one we mean by each. And then suggest at least 3 control variables. So then Frank argues, so maybe one of the students argues, that this experiment is an example of a chemical change. Do you agree or disagree? Provide reasons for your answer. So you need to substantiate. You need to provide some kind of substance to that. So I hope that starts getting you thinking. Draw out what we mean with these different rods set up around the Bunsen burner and consider what would be occurring here, identifying variables, etc. Let's move on and start to talk a little bit about physical change and chemical change. So I'm going to be giving you a summary, and that would be very helpful. I recommend you go and download the show notes, as Abram said, and follow with me on this. So, physical change. A physical change is something that can be seen or felt, but that doesn't involve the breakup of particles in the reaction. During a physical change, the form of matter may change, but not its identity. And the example I've got here is of a phase change. Now, all phase changes across the board, whether you're going solid to liquid or liquid to gas, okay, all phase changes across the board will always be physical changes, sorry. The reason for that is because, yes, we can observe a change. It can be seen or felt. So, example, a block of ice melting, going into liquid. You can physically see that block of that solid changing into the liquid. But it's still water particles. It is not involving the breakup of any particles. Okay? So, for example, phase changes of water. And the picture I've got at the bottom here very clearly indicates this is water molecules, obviously H2O, where you've got 1 oxygen and 2 hydrogens. And they're able to slide over one another. One of the models for a liquid, the particles are able to slide over one another. And here in the gaseous phase, they've moved apart and they're filling up the space of the container. But what you should notice is that whether it's in a liquid or a gaseous phase, it still is water. It's still H2O. The oxygen is still bonded with 2 hydrogens. So it hasn't changed its identity. The particles themselves, the atoms haven't separated or split up in any way, but rather the particles are just further apart from one another in this case. So it's not changed its identity in any way. So, a physical change. If we move across to consider chemical changes, when a chemical reaction takes place, so now we're considering chemical change, chemical reactions. What happens is that new substances are formed with very different properties. And maybe you've done an experiment with, you could have iron and sulfur particles mixed together. So iron filings and sulfur mixed together, that's just a mixture. That would be a physical change because you've put these things together. But if I was to bring a magnet close by, I could separate the iron filings away from that sulfur, which is non-magnetic. So we could very easily separate them. But if it undergoes a chemical reaction and changes to iron sulfide, now it's going to have very different properties. It's actually, I believe, non-magnetic. So the properties of the substance have changed completely, and that's helpful to note. So new substances are formed, always different properties. And I want to encourage you to go, if you've got the opportunity, to go and play on the SVET simulation. You can go and look at reactants and products and how balanced equations work, and so that might be very useful, particularly because you can see the particles and how they're rearranged. So maybe make use of that. I've got 2 examples of chemical changes, and the first is decomposition. So decomposition is referring to breaking down. If you think about it, if you do biology or life sciences, how decomposers break down and return nutrients back to the soil, into the atmosphere, etc. So decomposition, you're thinking breaking down. of hydrogen peroxide. Let's write it out in words, and I would write up here hydrogen peroxide breaks down into oxygen and water. So notice now the new substances are formed, and they will have very different properties from the original substance. But it's a breakdown. It's separated one substance into two others, at least two other substances. It's broken down further. In comparison, synthesis is going to be when things come together. So we had decomposition, which is breaking down. Synthesis would be things coming together, things forming, things being made. Okay, and think maybe photosynthesis. Photo was referred to light. Synthesis coming together. So photosynthesis, how plants maybe make food for themselves. So synthesis is coming together, forming, and the forming of water. How is synthesis done? Well, if you've got hydrogen and oxygen can together form water. So notice here I've got two reactants coming together to form one product. It's a forming together. If we turn and try and discuss these two equations in a bit more detail, we can represent them. So let's represent decomposition. So notice I've got a key here. The big one is the oxygen atom. The next one is the hydrogen atom, the little yellow one. And there I've got hydrogen peroxide. Now hydrogen peroxide's formula is H2O2. And you can very clearly see two hydrogen atoms and two oxygen atoms within that H2O2 molecule. So I'm writing up here H2O2. But what do you notice is that I've actually got two whole molecules of them. So I'm going to put, let's change color, I'm going to put a big 2 in front there. Okay, because each one has got two oxygens and two hydrogens. And we said it formed oxygen. So I'm going to drag this little guy across. That's one oxygen molecule. Absolutely perfect. Now we said it also formed water. So I would need an oxygen and two hydrogens. That would be an oxygen molecule and a water molecule. Is that sorted? Well, let's check quickly. When I say check, I need to check that I've accounted for all the atoms, because you know matter can't be created or destroyed. We've got to have the same number of each type of atom on the left-hand side and on the right-hand side, because those atoms can't have just gone nowhere. So notice I've got 1, 2, 3, 4 oxygen atoms. 1, 2, 3. Only 3 oxygen atoms on the right. So I'm going to have made another water molecule. And that's going to particularly help me, because I think otherwise I wouldn't get the hydrogens balanced either. Just count 1, 2, 3, 4 hydrogen atoms in the reactants, and now 4 hydrogen atoms in the product as well. So absolutely, that is definitely now balanced. And we can very clearly see it's broken down, and the particles are completely rearranged. The atoms are completely rearranged, I should say. Old bonds have broken and new bonds have formed. And that's helpful because it's clearly a chemical change. It's clearly changed from one type of substance into other types of substances with different properties. And I can very clearly identify here that the atoms have completely, old bonds have broken and new bonds have formed. Let's consider synthesis. I'm actually going to, before we do that, let's write a full equation for this. It formed water, O2, and there was one of them, and H2O. But how many of them were there? There were 2 of them. I'm just writing those balancing numbers, if you like, or stoichiometric ratios in a different color so that you can clearly identify, I'm counting how many molecules of each I've got. If we turn across to our synthesis, this was again oxygen and hydrogen, and I start with one oxygen atom, or one oxygen molecule, but it's diatomic, so 2 oxygen atoms, and 2 molecules of hydrogen, also each diatomic, and that was forming water. So 1 oxygen with 2 hydrogens, that's a water molecule, and then another oxygen, because remember I started with 2, so I must end up with 2. I have 4 hydrogen atoms on the left, and I must end up with 4 on the right. So notice I'm going to have to make 2 water molecules. Okay, and now is it balanced? Well, let's check it. 2 oxygen atoms, 2 oxygen atoms. 4 hydrogen atoms, 4 hydrogen atoms. Yes, it's balanced. Let's write up an equation for this. Well, we had oxygen, O2, and hydrogen, H2. Notice those are each diatomic because when they're by themselves, they bond together, okay, because they're so reactive. And those came together to form water, which was H2O. Check my numbers. We had to fill in. Well, it was 1 oxygen atom, so that's an understood one. I'm not going to write it in. And 2 hydrogen molecules, so 2 of those units, and it formed 2 water molecules. And this is very, very useful. Notice it's a synthesis. It's a coming together to form something new. Okay? And always, this would definitely be a type of chemical change. So we discussed physical change and we discussed chemical change. I think we need to stop and have a short break now. So mindset is get those thinking caps on and try that challenge question. Over to you.
Thank you so much, Tracy. And the notes are up on the page. It's facebook.com/learnextra. Like the page, share the page, of course, with everyone. And do send me some questions if you're struggling. We'll see you after the break. Welcome back, Mindsetters. Now I can see you guys are on the page, and thank you so much. I see Tekla is even posting some questions. Thank you so much, Tepang, Mishek, Lungelo. Thank you, guys. And if you're still struggling, send those questions. And let's not just send questions, Mindsetters. Let's also help one another. If you see a question on the page, help the other Mindsetter because we are in this together. We're working together. Remember, for you to win this awesome calculator, Casio calculator, all you need to do is to take the test yourself questions. The link is on Facebook. We have the notes that are on Facebook, so take the notes and then fill in the form on the test yourself questions, and if you get the right answers, you could win this awesome calculator. Tracy?
Awesome. Thanks, Abram. So mindset is do get thinking and challenge yourself with those questions. Let's go across to the last part of my summary, and I've drawn together a table for you just to compare physical and chemical change one last time. When we speak about physical change or chemical change and the arrangement of particles, physical change, particles may spread out or could come close together. But the bonds between the atoms do not change, will not break. So inside the molecule, for example, that water example, where we had 1 oxygen and 2 hydrogens, the whole molecules could separate, and so you're looking at intermolecular forces there. But within the bond between the oxygen and hydrogen is not breaking. Okay, it's not going to change its identity, and so that would be very, very important to identify. Whereas with chemical change, new compounds are formed. So their old bonds are broken, new bonds are formed. Okay? If we consider conservation of mass, well, mass must be conserved. The total mass, as well as the number of atoms and the number of molecules, will always stay the same, because if you think about it, they're just moving further apart, or they're speeding up, or they're coming closer together, but the number of molecules has not changed because this identity hasn't changed. In comparison with chemical change, the old bonds break, new bonds form, so the number of atoms must be the same, the mass must be the same, but the arrangement of those atoms is different. So therefore, the number of molecules could be very different. It doesn't always have to be, but it certainly could be. So mass is conserved, but the number of molecules may change. And if you think across to what we had there with the synthesis reactions, if you had two substances coming together to form one substance, then of course the number of molecules could very well change. Comparing physical and chemical change now in terms of energy. Well, for physical change, because you're just rearranging those molecules, energy changes are normally quite small. We say normally. Whereas for chemical change, energy changes are usually larger. Why? Well, because the old bonds need to break, and then energy is released when new bonds are formed. So significant changes in energy can be possible because old bonds are being broken and new bonds are being formed. Then lastly, in terms of reversibility. By reversibility, I mean can be reversed, can go in the opposite direction. Okay? So if I want to speak about a physical change like ice melting, how would you reverse that? Well, you would probably put the water back in the freezer, the ice tray back in the freezer, and that liquid would be able to be reversed back into a solid form. Okay? Well, in the same way here, physical changes are usually easy to reverse and significantly easier to reverse than chemical changes. Some examples: we could filter things, we could distill things, we could let the substance undergo some kind of temperature change to allow it to undergo that physical change that we're looking for. In comparison, chemical changes are going to be far more difficult to reverse because it's going to have to undergo a whole chemical reaction or a series of chemical reactions in order to get back to whatever that substance was. And some reactions are completely reversible and so do occur quite easily, but in comparison to physical changes, the physical changes are usually much easier to undergo. So I hope that gets clear in your mind the comparison between physical changes and chemical changes, and that you would very easily be able to identify, because that's what we're going to be practicing next. So let's tackle some questions. A child has been playing in the kitchen and starts playing with the salt and pepper shakers and maybe a glass of water or a bowl of water. And so mixes. Let's go. Table salts, peppercorns, and some water all together. Mom comes along, sees the mess, and says, no, we need to solve this problem. We need to separate these things out. So, to try and separate the substances, a number of processes could be done. We want you to think about ways that we could separate the peppercorns from the salt water. So, firstly, you need to think, what is going to dissolve? If I was to have this, let's say, a beaker or glass of water with salt mixed in it, the salt will dissolve. So the salt crystals have now formed Na plus and Cl minus ions, have gone into solution, and so they will have dissolved. Will the peppercorns dissolve? No, they're big lumps of pepper. They're not going to dissolve. And so my beaker would probably be like that, with Na pluses and Cl minuses. And I'm going to draw in these big lumps of the peppercorns. And maybe they'll float, maybe they'll sink. I'm not sure. Let's just put them all over the place. Across the board. So that's the mixture. How are we going to separate this? I've put Na plus Cl minus. I should also just put in here H2O and NaCl. So, how would we separate the peppercorns from the salt water? Well, I think it's important to note that the peppercorns will not dissolve. So, dissolve the salts in water, H2O, peppercorns won't dissolve. So how am I going to separate them? Well, I could pass this through filter paper or even some very fine material. Filter paper would probably be the easiest, so I'm going to write here filter through filter paper. And what's going to happen is that the peppercorns will be remaining behind. If I've now got my beaker with a funnel, okay, and through that I'm pouring the solution. That's going to go to the bottom, and the peppercorns are going to remain behind on the filter paper, okay, because they're going to get stuck. They're too big to pass through the very, very fine mesh of that filter paper. So, solved number one. We have got the pepper out. How are we going to get out the salt from the water? Well, now we've got our beaker with the water and the NaCl. Suggestions? Think about it. Well, if I want the salts, that's what I want out. I could evaporate the water and allow it to evaporate and escape, and so you would be left behind with the salt. And so that would be a quick answer. I could heat the salt water solution and therefore allow water to evaporate. I could even just leave that beaker in the sun, and eventually all of the water will evaporate and leave behind the salt crystals. Okay? Leave behind salt crystals. What about if I wanted the water and I didn't want the salt? Well, you could go through a process called distillation, where you heat the solution again, but then cool and condense the vapor that comes off, and that would allow you to collect the water. Identify each process as undergoing a physical or a chemical change. Well, think this through. Have we changed the substances in any way? Have we formed any new products? We still got the peppercorns. We've still got the salts. The water evaporated, but it still was water. So no, we haven't formed any new substances, so therefore it cannot be a chemical change. It's only going to be physical changes. So each process, well, all the processes would all be examples of physical changes. Okay, so the answer was definitely physical changes there. The next question, question 2. given the following equation, now immediately I want you to identify this is going from one substance into three different substances, one substance into three new substances, and they will have very different chemical properties as well. So the key here, even before I read the question, which I know is coming, is identify this as a physical or a chemical change. It's a chemical reaction, new substances are formed, it's a chemical change. So, chemical change. Identify this reaction as a synthesis or a decomposition. Well, are we making new things, forming new, are we building up, I should say, forming something, or is it breaking down? And the way you can identify this is by looking at the number of molecules that are made, specifically the number of different products that are made. So we started with one reactant and formed three products, which means this thing is being broken down into simpler forms. So definitely this must be decomposition. Decomposition. It was breaking down. Now show that the law of conservation of mass applies. For this you need a periodic table and a calculator, like that lovely Casio calculator. So go and do the test yourself questions. For this you need your calculator and you need a periodic table, because we're going to be looking at the mass of the products and the mass of the reactants. So I'm going to start with by writing the full equation down. So they've given it to us. We need to be very accurate as we write this down. It is NH4 brackets 2 CO3. So check that. Yes. And it formed NH3, and I think there were two of them. Yep. Plus carbon dioxide plus water. Okay. Now, just check that it's right. As you do this, we need to we were looking at the mass of the products and the mass of the reactants. So I've got a periodic table, and I'm going to go and list all of these masses. But I need to do them in the correct ratio. And this bracket is incredibly important, because notice it's saying it's going to be 2 of the whole ammonium ions. So therefore, 2 nitrogens and 8 hydrogens. And that's critical. So I've got a periodic table here. Nitrogen has a mass of 14. Hydrogen has a mass of 1. And I think, let's go, carbon has a mass of 12, oxygen a mass of 16. I've identified the various substances I've got. Let's go across here. We had nitrogen, and I'm going to put the 2 in the front and multiply that whole bracket. Okay. And let's write in, well, each nitrogen is 14, and there's 2 of them, plus 4 hydrogens. So 4 times 1. Okay? But the whole thing was 2. So I'm going to simplify this down. So surely that would be 14 plus 18. Yep. With a 2 in the front. And so, oh, not 14 plus 18. I'm doing the maths in my head. 14 plus 4, which is giving me 18. Which is giving me 18. That whole thing is going to be 2. To that, I must add 1 carbon. So carbon, if we go across, was 12. And there were 3 oxygens, and each oxygen is 16. So 12 plus 3 times the 16. Now notice I'm writing this out, and it might seem like a bit of a hassle, but what you're doing is you're identifying the mass of each substance. okay, and how much each substance is contributing to the total mass. So 3 times 16, let's grab our calculator. 3 times 16 is giving me 48. So across here, 48. And now I think I can do this whole thing. So it was 2 times 18 plus 12 plus 48. And I know it might look complicated, but let's go quickly together. So 2 times 18 is giving me 36. To that I'm adding 12. To that I'm adding 48. And that's giving me a total of 96. So the mass on this side is, my answer, I'm going to write it in yellow, 96. If you like atomic mass units. That is on the left-hand side. Okay. Now I want to go across to the right-hand side. And because I've written across the page, I want to work specifically with that side. I'm going to change pen color and quickly write up the rest. It was 2 ammonia, NH3, plus CO2 plus water. And now I'm doing the right-hand side. Notice I'm comparing left-hand side, right-hand side. So I don't want to write an equal sign between them yet. I want to prove the one and that is equal to the other. So very quickly, let's go. Ammonia. Well, I know nitrogen was 14. I know each hydrogen is 1, and so 3 multiplied by 1. Close my bracket. That is going to give me 17. But hold on, there were 2 of them, so multiply that by 2. To that I'm adding carbon. Carbon was 12. And 2 of the oxygens, which was each 16. Then 2 times hydrogen, which is 1 plus 16. So let's simplify this out. I've done that first part. 12 plus 2 times 16 is, I know, 32, plus 2 plus 16. Let's grab our calculator, clear this, and I'm saying 2 times 17 is going to give me 34. To that I'm adding 12. To that I'm adding 32. To that I'm adding 2 and another 16. And that's giving me a total of 96. So my answer here, what do you know, is that the left-hand side mass is equal to the right-hand side mass, which means that matter hasn't been created or destroyed. The same amount of matter on the left-hand side and the right-hand side. Yes, absolutely rearranged and totally new products, but the number of atoms of each type were exactly the same, and so therefore the mass is exactly the same. And that's what we mean by conservation of mass and conservation of matter. So I hope that's really helped you. Make sure you have a calculator and a periodic table when you do these types of problems, because it's very important to be able to compare them. I think we need to take a short break. So Abram, over to you.
Thank you so much, Tracy. I like the fact that you said we all need a calculator. Talking about a calculator, did you know, Tracy, that this awesome Casio calculator has the previous answer memory, which means unlike other calculators, if you have like the calculation that you've just done now, if you forgot the answer, the previous answer, you can just come back to this calculator and it will give you the answer.
Brilliant.
So it's awesome. So mindset is make sure that during this break you do the test yourself questions and stand a chance of winning this awesome Casio calculator. See you. Welcome back, Mindsetters. Now, if you just joined us now, you're a bit late, but you can still catch up. I know Tracy's a bit slow today because she wants you guys to understand. So that is the whole aim. So if you have some questions, feel free to throw them to me on facebook.com/learnextra. But also remember, we do have an active help desk on Facebook, which is an application which you can get, Mindsetters. Check out the FAQs that we have there and still submit your own questions. The link to that, it is apps.facebook.com/learnextra help desk. I'll post the link on Facebook. Tracy?
Thanks, Abram. So Mindsetters, we are thinking through the challenge question now, and I really hope that that you've thought it through since I posted and gave it to you at the start of the show. The question was all about a bit of an experiment. And in this experiment, we had students investigating heat conductivity. And this is certainly an interesting question because in a test or an exam, it's always very valuable to consider some of the practical components of science because, you know, science is all about applying stuff to the real world. And so we really want you to be able to think through these issues and visualize the scenario and answer and compare in terms of the scientific method. Now, when I speak about the scientific method, it's important that with the scientific method that we keep all other factors that could affect our experiment exactly the same and only change one thing. And when we change that one thing, we get a specific outcome. We get a result. And so we can get that result and compare and say, it was definitely that one thing that I changed that caused this effect. So that's what we mean by the scientific method. It's saying, what steps do I need to put in place that will be able to make sure that when I do an experiment that it's a fair test. And so you need to identify independent variables, dependent variables, or an independent variable, a dependent variable, and things that I must control variables that must be kept the same. And when you can do that, you can answer these types of questions. So let's have a look at this challenge question. They were investigating heat conductivity of various metals. They set up 4 metal rods of the same length, that's helpful, and they attached matchsticks at the end with little blobs of Vaseline. Now you all know Vaseline, that sticky stuff. They set up the rods equal distances from a Bunsen burner, so a heat source, and they took a stopwatch and they used that stopwatch to time how long it takes for the Vaseline to melt and causing the matchsticks to drop off the rods. Identify the independent variable in this experiment, the dependent variable, and 3 control variables. And then we're going to talk about would it be a physical or a chemical change. So I'm going to start by drawing not a 3D model, but just a quick sketch of how I think this would be set up. So I'm going to start with my Bunsen burner. Oopsie, let's try that again. With the Bunsen burner in the center. Okay, and there's a little flame on the Bunsen burner. Not the best Bunsen burner in the world, but hey, let's try the flame the other way around. Okay, and going away from this Bunsen burner, there are various rods. Now, I would imagine that we've probably got a tripod here, and on that tripod we've got maybe a type of wooden structure that could hold those rods away. But if you're imagining, and I'm going to actually undo those and try and not draw it in 3 dimensions, because we don't draw things in 3D because it's impossible, and we are science teachers, not art teachers, for a reason. I know my strengths, and I promise you it's not an art. So I'm drawing 1 rod, but imagine there's one on this side and there's one coming out the page and there's one on the back of the page. Attached to that, there's a little blob of Vaseline, and attached to that, there's a little matchstick. Okay, with its little match on the end. Having a look at this now, we've got our heat source, we've got the metal rod, we've got the Vaseline, and we've got the matchstick. What's going to happen? Well, over time, heat is going to travel through the metal rod. It's going to cause that blob of Vaseline to melt, and so eventually the matchstick is going to be on the floor or on the table. probably. It's going to fall off because the Vaseline is going to be a puddle of Vaseline at the end. Now, if we go back to the independent variables, what do we mean by independent? Independent is something that I change, I control, okay? And it's the one thing that I change in the experiment. What was it that I changed? Well, I treated everything else the same, but what did I change? I changed the type of metal. So maybe I've got copper, maybe I've got silver, maybe I've got nickel, maybe I've got iron, a number of different metals that could be investigated. And so the independent variable is the thing that, and I'm going to circle it and write here, I control. And it's very easy to identify because it's got the letter I starting it. It's the thing I change, I control, okay? And maybe I actually want to change the control bit and say I change. And what was it, the thing that I changed? I changed the type of metal. So specifically you're thinking, what did I do to investigate this? I had 4 different types of metals. Then what was the dependent variable? The dependent variable is the thing I measure. It's the thing that is the outcome, okay? And it's the easy way of thinking about it is that adults are independent and then they have children that are their dependents, that are relying on them for food and housing and love and support. The offspring or the outcome is going to be the dependent variable. It depends on whatever I control. So how would I investigate it? Well, surely I was measuring with my little stopwatch the time it took, whatever the time was, the time it took for the matchstick to fall. That is the outcome. And the one metal might be a very good conductor of heat, and so allow the heat to travel through very quickly, and so the time will be short. For another metal, it might be a very poor conductor or a poorer conductor of heat, because most metals are pretty good conducting heat, but it might take longer time, and that would be measured as the time it took for the heat to travel through. So the dependent variable is going to be variable is what I measure. It is the outcome. And so it is the thing that you measure. And in this case, what did we measure? Well, it was very simply the time taken for, well, the Vaseline to melt. How are we going to identify that? Rather, I would say, for the matchstick to fall. Because you are looking at, that's the thing I actually am able to physically measure. I measure the amount of time it took for the Vaseline to fall. Suggest 3 control variables. By control variables, we're meaning what must stay the same. Well, obviously, how far away from the heat source it must be, okay? Because if it's far away from the heat source, well, then it's going to take time for the heat to get to it, and eventually it will. But that's not going to be a fair test. So, definitely how far away from the heat source it was. The other thing I need to consider is the length of the rod. So I'm just going to take a different color and circle some of these. They set up the rods equal distances. That's a control variable. The rods were the same length. We had the same amount of Vaseline on each, because obviously if you have a big blob of Vaseline, it's going to take longer to melt and eventually cause the matchstick to fall. So those are the types of things that you're looking for in terms of control variables. What other things could affect my experiment. If they have any effect, then my experiment is no longer a fair test. And so you have to make sure that you keep everything the same. So control things, same length of rod, same blobs of Vaseline, equal distance away. And then the last one. Frank argues this experiment is a chemical change. Do you agree or disagree? It's definitely not a chemical change. It's a physical change because it's conducting heat. What could be and the Vaseline was melting, so that was also going to a liquid state. So definitely, no, all of those were physical changes. The only one thing that you could say is a chemical change is the chemical reaction of the combustion of the gas. But I would agree that those should all be physical changes. And so thinking through this, I want you to consider how you would answer experiment type questions. I hope that's really helped you, mindsetters. From me, keep well, God bless, and I'll see you next time.
Thank you
Thanks,
so
Barbara.
much. Thank you so much, Tracy. Unfortunately, we have to wrap it there. Mindsetters, if you still have some questions, make sure that you visit our app. It's apps.facebook.com/learnextra help desk. But from us, me and Tracy and the little one there growing, it's peace.